Oh, how are you guys doing? It's a beautiful day in the neighborhood, a beautiful day for a neighbor. Biomechanics 415. That is the class for me. All right, guys, let's talk about schedule, right? Snoopy. So we are here as per university guidelines. I am to give you nothing, so I can't give you any new lectures. I can't give you any assignments. I can't give you nothing. So basically, we're here. I do have, check your email. I do have a virtual office hours where I can clarify things, answer questions. We're going to do it right here on this channel on YouTube Live. And you guys can type in questions, clarifications. It could be about anything with class. And I will verbally answer that, and then I'll save it, and you can always go back and review it or check it. Okay, so this is what I wanted to show you. So here is where we are. No class, no class, lecture, 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 lecture or review, depending on how far we get. Moodle test. Last day of class where we make sure everybody's on the same page. Now, I have made a change that I'm going to post an email. Your final will not be some kind of custom project. I can't do that. The more I thought about it, students are going to want to bring, 80s to 100s, and it's going to have to be a test. And I'll tell you one biggest reason why is because you only had one test so far. So even though you're going to still have the same amount of grades being accountable for as the original, instead of 3 regular tests, you had 1 regular test. You're going to have a lecture confirmation a grade, and then you're going to have that 3rd grade test. So the 4th one, I need to kind of keep consistent with the syllabus and not vary it too much. So it'll be an optional final. If you think you can help, now it can hurt you if you don't know anything and you don't study, but it's going to be an optional Moodle test, and that way you can decide if you want to improve your grade. But if I do a project, then I'm just going to have to look at a ton of projects, and it's going to not, it'll defeat the purpose. So the optional final will be a content-based assessment, and it'll be more like the original syllabus. All right, boys and girls, today the confirmation is going to be Happy Easter. Okay, Happy Easter. And I know darn well some of you, not even some of it, because if you don't watch these things, you're not even watching me say this right now. Some of you look at the comments and say, "Oh, Happy Easter," and they put out it, but I don't care. I don't care right now. So let's get to the brass tacks. This should be review. However, I'm going to emphasize key points that you guys need to know for biomechanics. Basically, why is this important to we as biomechanists? Are therapists who apply biomechanics, or physical educators who apply biomechanics, or chiropractors who apply biomechanics, or athletic trainers who apply biomechanics. So basically, this is the biomechanical part of what your future job is going to be. We need to be able to see vectors. And remember that forces are vectors, motion is vectors when it takes direction into account. And this is a 2-dimensional plane. So obviously the 3rd dimension is depth. Can't draw that on a 2-dimensional piece of paper, so we take what we can. And the concept of vectors is no different than north, south, east, west. And you know darn well you can travel in a direction of northeast, northwest, southeast, southwest, and all that stuff. But the key thing is, if you're traveling northeast, for every 10 miles you go, how much of that was traveling north? For every 10 miles you go, how much of that was traveling east if you're traveling northeast? Well, it kind of depends. Were you shallower than steep? Were you steeper than shallow? Were you right down the middle? So if you know you're traveling northeast and you travel 10 miles northeast, how much of that 10 miles is actually north and how much of that 10 miles is east depends on your angle, right? If your northeast is very shallow, it should make sense that you're going to be traveling for that 10 miles, you're going to be traveling more east than north if you have a shallow angle. And if you have a steep angle, you're going to be traveling more north than east. Kind of common sense, right? That's what this lecture is about, man. It's about common sense. So the first thing we're going to do is talk about how we grid directions and vectors, and that's with what they call a Cartesian plane. And this dude Descartes, way back in the old days, was trying to describe where a spider was on a ceiling. So that's a two-dimensional, your ceiling is 2 dimensions, and so he imagined this quadrant system where he could describe, this many points here, this many points there, and that's the whole plot graph, right? Where you plot things, you put little points there. Okay, that's what this is. So for the Cartesian plane, a couple things that we need to make sure we're on the same page. You should have trigonometry already before you took this class. So again, this is me cherry picking the important parts about it that you're going to need to know when you apply your biomechanics. So the first thing to remember is that the Cartesian plane is there to help us with kinematic direction, positions, and also kinetic as well. Meaning that you take these two axes, the x's and the y's. If you notice, a typical graph may see this, right? So this is 4 graphs. You could kind of look at it like that. These are 4 independent graphs that cross-section x's and y's. Remember, x and y are straight line directions, but positive y, positive x, positive y, negative y, positive x, negative are specific directions in that dimension. What do we see here? First of all, in anatomical position, right? We have this anatomical position, a universal starting point in biomechanics, or an anatomical kinesiology. Well, we have an anatomical position in regular mechanics as well when it comes to trig, and that's here, positive x. Positive x is 0 for us, and we have a term for that, from the horizon. So you think about you're on a beach and you're watching a sunrise and you can see the horizon. That's the across, where the water meets the sky, the horizon. So FTH, you need to know what that means. You need to know what FTH stands for, from the horizon, and that's 0 degrees, or that's positive x. So how we communicate vectors is magnitude and direction, okay? We give direction angularly with angles from the horizon. So in other words, if my northeast were very shallow, I would communicate that I'm walking 10 miles northeast, 20 degrees from the horizon. You see how that works? 20 degrees FTH from here, because if all I said is I'm walking northeast 20 degrees from what? What does that mean? 20 degrees from where? So we have a reference point. All of our angles are going to be referenced from this kind of biomechanical anatomical position of positive x, or 0. So 20 degrees from the horizon, 30 degrees from the horizon, 45 degrees from the horizon, 80 degrees from the horizon, 90 degrees from the horizon. So we know that x and y will always be perpendicular to each other. They have to be, because they're in that right angles, right? So from the horizon, 0 degrees positive x, it's 90 degrees till I get to a new direction. All of it in one direction, positive y. And then if I continue to rotate another 90 degrees, then I get to the polar opposite of 0, and that's 180. So that's why, in layman's terms, when you change your mind, or when you go the exact opposite direction that you were going, they say that's pulling a 180. So I was, I made up my mind. I was going to buy this, and then I changed my mind and I went the other way. That's what that means. So this 180 literally means 180 degrees from here. Okay, so these are kind of like globally referenced, if you will, right? From 0, 90, 180, 270. Now we can go locally referenced, right? So in other words, I can say 20 degrees from 90, but that's the same thing as saying 110 degrees from 0. We're going to get to why we want to make things local when we get into the specific quadrants. But keep in mind, global references, we talked about that in 310, and then local references are going to be within the 90 quadrants. So 180, that's negative x. 270, negative y. What does 270 mean? Well, it's 90 from 180, or literally 270 degrees from 0. And then if we do an entire way around, you know what that number is. 360, right? Doing a 360 and spinning all the way around. 360 brings us back to where we started. Now, again, a few important things to remember here. If you had a force, and let's say the force was 500 pounds, all of that force has 360 degrees of options of being applied relative to positive 0. I mean, I could apply that force. Let's say I was pulling on something. I was pulling from something on the ground. I mean, I could pull shallow. I could pull steep. I can pull the other way. I could pull over here. I could be pushing down, so it could be down here. If I'm pulling, it's probably going to be up here. If I'm pushing, it's probably going to be down here. But I could pull with something with a down force. The point is that only 4 times out of 360 will all of my force be x or y. Positive x, positive y, negative y. Only 4 degrees. 0, 90, 180, 270. So statistically speaking, odds are that force is going to be applied either northeast, northwest, southeast, southwest. In other words, in a combination somewhere in here. There's 356 degrees of possibility. Think of it like that. So if I have a force of 500 pounds and I measure the angle that it's being applied, we have equipment we can measure magnitude with, we have equipment we can measure angles with, but you know what? You can eyeball it too. There's nothing wrong with eyeballing things. Coaches and therapists do it all the time. And the more we eyeball things, the better we get at it. So imagine having a force that's being applied very shallow. Just like our distance, if we walk 10 miles and it was at a shallow angle, most of that 10 miles was across and very little of that 10 miles was up. How much did we travel east? How much did we travel north? Same thing as with forces. If the force is being applied very shallow, a majority of that force is going to be x, with a little bit of that force being y. If that force is applied very steep, we're going to have most of that force being applied up, very little of it being applied across. And if it's right in the middle, 45 degrees is halfway between 0 and 90, then the same amount of across force is going to be equal to the up force. They're going to be the same. Okay, so that's point number 1. Think of it as if I have a basketball goal. Let's say this pencil represents a basketball goal, and this is the backboard. Okay, this is the rim, because we know a basketball goal is 10 feet high from the floor to the rim. The point is that if I have a basketball goal that I'm about to erect at the house, it's 10 feet across, and when it's laying on the ground, all 10 feet is in the x, none of it is in the y. Okay, all of the resultant is in the x. As I go to raise the goal up, I want you to notice something. It gets less and less and less long until there's nothing in the x. And at the exact same time that it's getting less and less and less long, it's getting more and more and more tall until all of its height is y and none of it is x. So there is a relationship there. In other words, I can't change the angle of the basketball goal and not affect the sides, the component sides of the x and y. So there's a relationship between resultant and vector. As one goes up, the other goes down. As one goes down, the other goes up. So think about that. What affected what? Change in angle. The angle of the basketball goal affected the x and the y component. That's trigonometry. That's what trigonometry is, guys. Trigonometry is the relationship between changes in that angle and the x and the y sides that it affects. You can't change an angle without messing with the vector components. Okay, we're going to get to that in a little bit, but I wanted to introduce that to you. So let's get back to our so what of our Pythagorean. Pythagorean's coming up a little bit of our Cartesian plane. So the key things to take note is in quadrant 1, meaning that if any resultant, whether it's force, velocities, accelerations, anything that deals with x and y, if it's applied in quadrant 1, the x component is going to be positive and the y component is going to be positive. So anything that happens between these two lines, x is positive and y is positive. Another thing is that at 45 degrees, the x amount and the y amount will be the exact same thing. Why? Because at 45 degrees, it's neither closer to x or y. It's right in the middle. Right in the middle. It's neither shallower nor steeper. So right at the middle, 45 degrees in between these two x and y is going to be equal. So what I'm going to teach you is any angle below 45 degrees in that window, x has to be greater than y. And any angle steeper, y has to be greater than x. Should be common sense, right? In quadrant number 2, if any vector is applied into quadrant 2 over here, now that's kind of like northwest, right? In this quadrant, the x is going to be negative and the y is going to be positive. Okay. In quadrant 3, so 1, 2, 3, 4. In quadrant 3, x is going to be negative, y is going to be negative. So in quadrant 3, negative, negative. Quadrant 4, positive, negative. Okay, x is going to be positive, y is going to be negative. Why is direction important? Well, vectors have magnitude and direction. So if we're talking about forces and velocities, you need the magnitude, how much, and you need where it's going, the direction. So that velocity needs to be reported in terms of negative x, negative y, positive x, positive y. It's not that you owe someone velocity. It's not that you owe someone force. It's the direction. The negative and the positive is the direction. Okay. So that is the key thing. If you need to pause it, there's a good slow picture of it for you to pause and apply. Okay. Now, speaking of Pythagorean theorem, okay, a squared plus b squared is equal to c squared. What in the world does that mean? It's a relationships between sides of right angles, right? Right triangles. And you say, well, dude, what does a right triangle have to do with vectors? Well, here's my y, here's my x. If I look at any quadrant, whether it's this quadrant, this quadrant or that quadrant, x and y will always be perpendicular to each other. They have to. X and y will always be perpendicular. So there's our 90-degree. There's the basis of our right triangle. It's the concept that x and y must always make a 90-degree angle. That's kind of cool. So they have to be perpendicular, therefore they have to form the 90 degrees. Therefore, the resultant will cap off our 90-degree triangles. Okay, so that's why trig works with vectors, because x, y, and if you go in super crazy z, they all have to be at right angles to each other. Okay, so Pythagorean theorem only looks at the sides. So it looks at the relationships of the sides of a right triangle. So in other words, if you have, in here you have the y, and then here you have the x. So I'm going to do it like this first, though. But notice how the marker doesn't reach the ends, right? Because the opposite side of the right triangle, the hypotenuse, is the biggest side, right? So even if all these three were the same length, when we go to do this, whoa, I need more of it. Okay. Now, the reality is that for our trigonometry for biomechanics, our resultants will actually be here. So in other words, let's say I throw a ball at an angle, and let's say I throw it with a speed of 70 miles an hour, but I'm trying to calculate its velocity, its directional speed. So if I throw it here with a speed of 70 miles an hour, I need to know how much of that speed is going in the x and how much of that speed is going in the y. So I'm trying to figure out how much of that speed is going up, how much of that speed is going across, and then literally here is the speed. It's my resultant. The marker is literally how I released it. And trigonometry is going to help me figure out how much of that speed was here, how much of that speed was here. And when I give it magnitude and direction, that's why we call it velocity. Once I figure out how much of it was in the x and how much of it was in the y, these are my vector components. So here's the cool thing, guys. Here's the magic. This doesn't look like a right triangle, right? It looks like some kind of claw. On your computer, you're able to do cool things like click and drag. And we do the same thing in biomechanics. What I mean by that is, as long as I don't change anything about this pencil, meaning I don't change its angle and I don't change its magnitude. Remember, in trigonometry, our vector arrows represent a lot of things. The arrow literally represents the direction wherever it's pointing. The length represents the magnitude, so smaller arrows are smaller vectors and bigger arrows are bigger vectors. Now, those kind of things. So my point is that as long as I don't change anything about this pencil, its magnitude or its direction, I can actually click it and drag it and move it across. And now I have my right triangle. Why? Because x and y will always be perpendicular, even if I click and drag my y. Look, it's still perpendicular. I still have a 90-degree angle. Another cool thing is I could click and drag my x. It doesn't matter. It's two different forms of the same thing. I could click and drag my x. Now look, x and y is still perpendicular. There's my 90-degree triangle. So you can't escape it. With vectors, with x's and y components, there's always going to be a 90-degree triangle in there. We just have to see where it's at. Okay, and the easy one to find is the 90 degrees because it's going to be the x and the y. Okay, x and y. Click and drag. Click and drag. Okay, so the Pythagorean theorem, a squared plus b squared is equal to c squared. Notice that they're squared. A is a side, right? B is a side, and C is the hypotenuse. But notice it's not a plus b is equal to c. It's a squared plus b squared is equal to c squared. One way to look at that is if you were to, let's say you were to walk. Let's say you were to walk 10 miles. We're going to use our same analogy as earlier. I'm going to walk 10 miles. And let's say you walk 10 miles northeast. And you know some of that 10 miles was, if you actually walked X, made a right-hand turn, and then walked Y, you would actually walk more than just going straight there. So the point is that X plus Y without squaring will always be greater than the hypotenuse. For that very reason, because X plus Y is a longer distance than straight there. Okay, so that's why you got to square them. When you square them, the math works out. But you don't just say a plus b is equal to c. It's a squared, b squared, c squared. So that's a cool check. I'm going to teach you guys when you're checking your trig. That's a good check, because when you calculate your components, your x and y components, they should be greater than the hypotenuse. So in other words, if I have a 500-pound force being applied at an angle, when I figure out what the x component is and I figure out what the y component is, the sum of the x and the y should be greater than the hypotenuse, unless I square it. If I square it, then x and y squared equals h squared. Okay, so why does it work? It works because x and y, in this case I showed you a and b, are always perpendicular. So here I have a force being applied to an object at an angle. Notice how some of that force is in the x, some of that force is in the y. This doesn't look like this. Well, not yet. All I got to do is click and drag, bang, right triangle, same directions, up and across. I could also click and drag like this, bang, right triangle, same directions, up and across. Okay, so that's how it works. In your book, I have some practice questions. This is your homework the next couple of days, okay, before you get off for break. And remember, you guys should have had trigonometry, and your calculators have this feature also. I just want to make sure you know it. Maybe, hopefully you did, maybe you didn't. If you didn't, it's all good. So if you got to turn your calculator off lock so that it can rotate. But this is a normal calculator, right? It just has multiplication and division. But when you turn that sucker on its side, some extra cool stuff happens. And you see sine function, cosine function, tangent function. Now, tangent is, remember how I said there's a relationship between angles and sides? I gave the basketball goal as an example. All of the side is x, none of it is y. As I change the angle, I change the sides. In biomechanics, the things we are going to be able to eyeball or measure is going to be magnitudes, like forces, velocities, and then we can eyeball angles. If you have fancy equipment, you can measure the angles. But the point is that we typically have to figure out the vectors. We're given these big numbers that have a combination, and we can either calculate or figure out the angles, and then we have to extract. We have to say how much of that was x, how much of that is y, which leads us to use sine cosine function a lot. Tangent is you have the sides, you have the x and y, and then you're trying to work backwards to the hypotenuse or the angle. We don't typically do that. We're trying to figure out the sides. We're trying to figure out the x and the y. We're trying to figure out the a and the b. We measure the c, or we measure the hypotenuse, and then we measure the angle that it's being applied. So we measure the hypotenuse, we measure the angle. Now, how do we know it's always a hypotenuse? Because of odds. Remember, it's very rare that all of any magnitude is going to be perfectly positive x, perfectly positive y, negative x, perfectly positive y, perfectly negative y. Even when you do a vertical jump and you think that all of your force is going up, if you drift an inch forward, back, side to side, it was a lot up, but it wasn't perfect up. There was a slight shallowness to it. So it's rare, it's hard to be perfect with your application of your force. Or again, even with your velocity, throwing something perfectly up. Try that. Take a ball and try to throw it perfectly up in the air. If you catch that ball in any position, it didn't perfectly go up, okay? So that's what we're getting here, is that in biomechanics, we're going to be measuring hypotenuses. We're going to be measuring resultants. We're going to be measuring the angles, whether that's the eyeball test or with equipment that can measure that angle, and then we're going to extract the x and y component. Now, why is that important? Because we can't apply Newton's second law unless we can compare apples to oranges. Now, you could compare apples and oranges, they're both fruit. You know what I'm trying to say. So in other words, if I'm looking at F is equal to ma, I can only do that for x forces and y forces separately. Only x forces will influence x motion, and only y forces will influence y motion. X forces plus y forces can influence combinational motion, okay? But the y force did not make something move across, and the x forces didn't make anything move up, okay? So that's why these combinational forces have to be extracted into their x and y component, so that now we can look at x forces x motion, y forces y motion. That's why it's important, okay? So you guys, for practice, go through on your workbook, on your book, and y'all, there's a ton of examples, and all of those examples are meant for a purpose. In other words, all of your examples give you a quadrant 1 force that's shallow, a quadrant 1 force that's equal, a quadrant 1 force that's steep, a quadrant 2 force that's steep, a quadrant 2 force that's equal, a quadrant 2 force that's shallow. Quadrant 3 that's shallow equals steep, okay? Now, your calculator will do the trigonometry for you, but I'd like for you to know kind of how, what I mean by that is if I'm in quadrant 2 and I say a force of 500 pounds is being applied at an angle at 100 degrees from the horizon, well, that drifts me into quadrant 2. In other words, am I there yet? No. Am I there yet? No. Am I there yet? No. I'm at 90. Am I there yet? No. I need to keep going. I need to go 20 degrees past 90. So as you can imagine, an angle of 120 degrees doesn't yield us a 90-degree angle. So you have to make it so, meaning that once you drift off into quadrant 2 and then you find yourself there, then you say, oh, okay, quadrant 2, and I'm 20 degrees from 90. That's another way of saying 110 degrees from the horizon. Well, when I am here, whatever my y component is, it's positive, and whatever my x component is, it's negative. So my point is that now you have to look at this triangle locally within these borders, within these boundaries. You no longer look, 110 just gets you there. Once you're here, then you're like, okay, this is 20 degrees in this box. Man, I'm a lot steeper than I am shallow. So whatever my y component is, it's going to be greater than my x. Whatever my x component is going to be less shallower than my y. Other things we know, the x component is going to be negative, the y component is going to be positive, and my y component is going to be greater than my x because I'm steeper than shallow. Okay? So you put in the trig numbers, just like you were taught in 207 or equivalent, you turn the crank, and remember what you're getting here. 500 pounds, how much of that is in the y, how much of that is in the x? That's all we're doing here. We're taking a resultant, an amount that we measured or I gave you, and we're saying how much of that is y, how much of that is x, and then we're capping it off by giving it the direction. Okay, so that is your homework to practice over the break. Let's do one together. Okay, I didn't prep this. We're just going to figure it out together. A force of 500 pounds. Well, I prepped the question, but I didn't prep the answer. A force of 500 pounds, and that little angle, that's angle theta, is being applied at an angle of 70 degrees from the horizon. No problem. Let me take a look at what that would look like. 70 degrees. That's kind of steep, right? That's past 45. So my y is going to be greater than my x. I know that already. So let me just try to rough draw it 70 degrees. Okay. So this is what I know. I know that my x component is going to be positive and my y component is going to be positive. But looking at it right there doesn't give me a triangle. I got to click and drag something to make my triangle. So I'm going to keep my x and click and drag my y to make my triangle look something like this. Ooh, shaky lines. This is my y, this is my x, this is 500 lbs, and this is 70 degrees. I'm saying the same thing. My hypotenuse is 500, my angle 70 degrees. I don't know what my x and y is yet. That's what I need to figure out. That's what I'm asking. I'm saying, hey, how much of that 500 pounds is across and how much of that 500 pounds is up? So with our basic trig, I know that the sine function is directly proportional to the opposite side over the hypotenuse. Well, if this is 70, who lives across the street? Who lives on the opposite side of the street, right? 70 degrees, opposite is going to be my y. Adjacent means who's touching you, who lives adjacent to you, someone who shares a border, right? Someone who shares a property line. So in this case, x is going to be adjacent. So my sine function is going to be the opposite side, in this case my y, over my hypotenuse, which is 500 pounds. The sine of 70 degrees, because that's my given angle. Then I'm going to take my calculator. I'm going to make sure I rotate it so that I'm on the fancy trig part, right? And I'm going to put in 70 sine, and I'm going to get a decimal place. 0.93. Now, you know what that really is? That's percentage. It's percentage, meaning that you know how that's very steep? That is your when you do 70 sine, that's your calculator's way of saying, hey, in trig, 93.9% of that 500 pounds is in the y. That's what that means. That's what that decimal place means. So what you're going to do is you're going to say, okay, that's cool. Well, 93.9% of whatever the resultant is going to be in the y. Well, what is the resultant? 500. So that's why you cross multiply times 500, and you get 400. Y is equal to 469.8 pounds. But that's not enough. We got to give it direction. What is the direction? Positive, up. Okay. So the y component is 469.8 pounds. Not really caring about decimal points. So what does that mean? That means when I apply a force of 500 pounds at an angle of 70 degrees, a big chunk of it is up. That's what that means. Now let's figure out how much of it was across. Well, for adjacent sides, we've got to use the cosine function, if you guys remember that. So the cosine of 70 degrees is directly proportional to the adjacent side, that's my x, over 500 pounds. Now watch this, how cool, okay? 70 cosine, look at that decimal, 0.34, 0.342. It's a lot smaller than 9.6, right? Because it's shallower, right? I'm sorry, the resultant is steeper, meaning that the x component is going to be smaller. That tells you that the x is going to be smaller than the y. The y was 90-something%. This is on 30-something%. So let me do the math. 34% of what? Times 500 pounds That gives me x is equal to 171, and its positive direction matters, pounds. So the x component was only 171 pounds. That's how much of that 500 was across. So here's the point. X forces influence X motion. Y forces influence Y motion. So most of that 500 pounds is going to be trying to influence motion in the up and down. So the point is that if you're actually trying to move something in the up and down and you're applying your force at an angle, you have wasted force. Not all of that 500 pounds is trying to move whatever you're trying to move up and down. You're wasting energy. Okay? That's why this is important. You don't want, when you're working with a client, working with an athlete, you don't want to have wasted energy possibly. So you got to see angles of application and say, well, I know how we can improve by better mechanics. What does that really mean? Being more efficient with your energy production. Now, going back to something I wanted to check, where you could check yourself. So let's think about our x, y, and z. So x equals 171 pounds, y is 469. But if you add those two together, if you do a plus b is equal to c, if we don't square them is what I'm trying to say. 469 pounds plus 171 equals. So the x and the y equals 640 pounds. That's a lot more than 500, right? That's okay. That's okay. The x plus the y is always going to be bigger than the shortcut. X plus y is always greater than the hypotenuse. A plus B is always greater than C. Pythagorean only works when you square the son of a guns. Okay? So that's actually a check when you're doing your trig. When you extract your x and y components, they should be greater. They need to be greater than the hypotenuse. Now, you could say, well, Dr. Campbell, isn't there 4 exceptions to that rule? Meaning that what if I supplied a 500-pound force perfect at an angle of 90 degrees from the horizon? Meaning that at 90 degrees, all of that force is in the positive y. Well, y, x plus y would equal to c, or a plus b is equal to c. 90 plus 0 is equal to c. 500 plus 0 is equal to 500. No, because if it's a straight line, there is no right angle. There's no angulation if it's a straight line. Remember, this is all about right angles. So if everything is y, you have no x. And if it's a straight line, you have no right triangle. Any angle that involves a combination of x and y, the x plus the y will be greater than the hypotenuse, because it must be. Okay? So your homework is to do all of those trig problems. Remember, my job isn't to teach you trigonometry, it's to try to make sense of it in terms of application of biomechanics. And that's the key, to summarize. The importance of it is, in biomechanics, we're going to be able to measure things, and we're going to be able to measure other things, or at least eyeball it. Resultants and angles. That's what we can measure. That's what we can get. And then once we have resultants and angles, then we can use trigonometry to extract x and y components. Okay. Also, to summary, your Cartesian plane, quadrant 1, 2, 3, 4, positive, positive, negative, positive, negative, negative, positive, positive. Also, keep in mind our angles within angles, halfway, 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 halfway. Anything steeper is going to be y more than x. Anything shallower, x more than y. X plus y needs to be greater than the hypotenuse. All different ways to check yourself, okay? All right, so reminder, if you're watching this morning, I'm going to have office hours on YouTube Live for biomechanics. It's going to be at 10:30 Wednesday. April 8th. Okay. You guys have a great day. Your code word for today is Happy Easter. Happy Easter, everybody. Make it a good one.